Well, everything is fine? Okay, just a second. What is just happening? So everything is fine, children? Am I in live? Yes, 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 yes. Perfect, perfect, perfect. Yes, 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 yes. Okay, 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 fine. Yes, 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 yes. Come on, quickly join, children. Quickly join, join. Yes, yes, yes. Hi, hi, Satvik. Hi, 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 hi. Hello, good evening, good evening. How are you? Just a second. Let me check. Let me check. Every- Yeah, yes, yes. It's perfect, perfect. Yes, yes, yes. It's seen. Yes, hi, 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 hi. Harshida, hi, Harshida. Hello, hello, Jati. Okay, I cannot pronounce the name. I'm sorry. Yeah, crazy girl Grishu. Hi, 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 children. Hello. Good evening, everyone. How are you guys? Okay, how are you? How are you? How are you? I don't know why I'm still saying that as watching is one only. I don't know why it is like that. Okay. So what is that language? Basically, you're chatting something in the chat box now. What is that language? Hi, hi, children. Hi, 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 hi. Hi, guys. So welcome back to Physics Wala. Physics Wala English Medium. Today is our lecture 2 of the 11th chemistry. We are going to discuss about the atomic structure. So quickly, please do join the session fastly, children. Please do join the session fastly. So we can start our session. Okay, great. I don't know why that is happening. Like, it's fine. It's fine. Ostana? Ostana. Okay, fine. Such me. Such me means is it true, right? That's the meaning, na? Yes. Yes, yes. Perfect, perfect, perfect. So shall we start today in the session? We will be discussing about it is a one shot of our atomic structure. We will be discussing all the important points of the atomic structure. So we will be starting with the so you remember about our some basic concept of chemistry. You remember about it? We discussed about the some basic concept of chemistry. Remember? So after that we are going to discuss today about the atomic structure. Okay. Shall we start our structure session? Shall we start? Shall we start our session, children? Everything is fine? Everything is fine from my part. Ma'am, this video is lecture. Good evening, Ujjwal. This video is lecture 1 or 2. This video is basically not lecture 1 or 2. It's basically a one shot. Okay, it's basically a one shot of the atomic structure. Okay, this before that we done with the some basic concept of chemistry. So this is going to be atomic structure. Okay, perfect. Yeah, रहने जब तक. No. Children, if you're talking something, please do talk in English because I can understand Hindi, but I'm not able to talk. Okay, when it comes, especially when it comes to typing, it's really difficult. Good evening, Ujjwal. It's good evening, right? So in the session, we are going to discuss about the atomic structures. We will be discussing about the. We will be start with a particular anode ray and cathode ray formation. Anode and cathode ray we will be discussing. Then we will be also discussing about the various concepts of the atomic structure. Then we will be discussing about the Bohr models of atoms and all those things which is comes as electromagnetic radiation. All those things we will be discussing. Okay, duration of the lecture is max to max. It's going to be 2 hours. Okay, max to max 2 hours it will be. Okay, we will be starting with 4 o'clock and we will be ended by 6 o'clock. Max to max. Shall we start our session? Shall we start our session? Please do let me know in the chat box. Shall we start our session, children? Okay, perfect. Okay. Okay, children. Okay, fine. So, what we will be discussing about something which is called as the introduction portion, which you go already know. We discussed in the some basic concept of chemistry also. The introduction portion we already discussed. What was the introduction portion? You remember about the introduction portion? What were the things which we discussed? We were discussing about, ma'am, what was the atoms, everything, right? So, it was actually according to the Dalton atomic theory. It was actually according to the Dalton atomic theory. Every matter is composed of extremely small particles. Any matter which will be consist of extremely small particles which is called as the atoms. And you can say that this atom is actually consist of again the extremely small particles, which is subatomic particles, which is going to be your electrons, protons and neutrons. Am I right? There also we have also known about this, right? In some basic concept also we discussed about it, right? So electrons are the, neutrons are the, protons are the, and I told you during that time we will be discussing how this how the particular how can we find out, okay, what is this particular one electrons, how they find it out. There is, okay, there is electrons as the, there is protons are there is something which is positive charge, there is something which is negative charge, there is something which is not charged. So those things we will be discussing in this chapter, okay, in this session. The particles are regarded as fundamental particles. All the electrons, neutrons and protons, all these are considered as the fundamental particles. Ma'am, notes kaha pe milega? Okay, note kaha se milega means, I guess, where will you guys get the notes, right? That is the correct answer, na? I mean, that is what something you are asking, na? You will be getting the notes in the app. Okay, you will be getting the notes in the app. You can just download it and you can fetch the notes. Okay, so now structure of the atom means, these are the things which you already know, right, children? You are studying that from the very young age itself. Okay, when an atom, thank you Aish Kumar, when an atom is there, we can say that they will be having this particular neutrons will be there and the electrons will be revolving around there, and there will be, you have the protons also. I mean, in the neutrons only you will be having the protons also, and the electrons will be revolving around them. So this is something which is nucleus. Inside the nucleus you have the protons, and the electrons will be revolving around the protons or the nucleus. These are something which you have already known, right? These are something which you know, right? Clear? Ma'am, Naveen, Karthik, ma'am, is this for the NEET? No, Kanna, this is not for the NEET. It is basically for the CBSE level. Okay, it's not that much NEET level explanations. Okay, so now comes the discovery of the electrons. Discovery of the electrons. The electrons were discovered by conducting an experiment by using a simple apparatus, which is actually called as the, it's usually in your textbook it is given as a discharge tube. Okay, so what happens means, you know what is the charge of the electrons? Electrons are negatively charged. They do have some mass and they do have some properties. So electrons are negatively charged. How these electrons are discovered? Okay, how these electrons are discovered? This is actually your discharge tube experiment. So you can see that there is a negative portion of the battery is connected to the cathode, and the positive portion of the battery is connected to the anode. And you can see that there are some light rays, or there are some rays are coming from the cathode and it is hitting to the anode. Do you know this experiment? Why you are not there in the English NEET channel? Okay, this is like it's I'm taking for the paid batches now. So Naveen, you are really, why you are Naveen, Karthik? Okay, it's fine. We will be adjusting it like this. Okay, it's fine. It's fine. Not able to see the chat also. Just a second, children. Okay, so first of all, cathode, that is, we are going to discuss about this particular anode discovery. Electron discovery. Okay, so what happens means, this particular discharge tube, they do have a tube that is consist of this particular sealed glass. So what happens means, we can see that there will be a particular glass tube is there, and that two ends of the glass tube is connected to, they do have the electrodes, and that is connected to the particular batteries. So this is a basic model of this particular discharge tube. Okay, children, clear? Okay, so now what happens means, the tube is also filled with a gas under study, and the two electrons are connected to the source, which is having the high voltage. So what happens means, the thing is, they will be that tube is actually, they will be filled with a gas. Yes, perfect, they are filled with a gas, and they do have two electrons, and that electrons will be connected to the high voltage, which is your battery. Okay, this is the initial setup. Now what happens now, they started to change the pressure inside the tubes. Okay, what they have done, they started to change the pressure inside the tubes. So apparently they started with the minimum pressure only, one, then slower the pressure. When it is reaches to a particular pressure, that is like 10 raised to -2 -4, like 0.00, like minimum pressure, very less pressure. What happens? Do you know what happens there? Any idea, children? What happens there? What happens there? So when the discharge tube contains the gas is at 1 atm pressure and high voltage, the gas remains non-conducting. So I told you, whenever they started to decrease the pressure, if it was 1 atm pressure, what happens? There was no change for the gas. Okay, the gas was not conducting any electrons, nothing was happening there. But when they decreases, the pressure of the gas is reduced. As I told you, the pressure is reduced. What happens? 10 raised to minus 2, which means they reduced. What happens? Slowly the gas started to conduct, and as a result of this, the light is emitted by the residue gas in the tube. Are you getting my point? So when it was 1 atm, what happens when it is 1 atm? There were no change for the gas, or there is no conduction for the charge gas. Now when they changes the pressure, or when they decreases the pressure, what happens? Slowly when the gas started to conducting and the light was emitted by the particular residue gas in the tube. Now we can say that the color of this particular light emitted, or the color of this particular one, is depends upon the what is the nature of the gas. Okay, so this was the initial setup they done. When they decrease the pressure was initially, tell me, 1 atm or 10 raised to minus 2 is less? Tell me, 1 atm or 10 raised to minus 2 is less? Of course 10 raised to minus 2 is less. So when the pressure is started to change or started to decrease, what happens? There is a change and the gas gas becomes conducting. Clear everyone? Clear? Now what they have done is, when the pressure of the gases tube is further reduced, what happens? When the pressure of these gases in the discharge tube is further reduced, the glow becomes weak. But at 10 raised to 4, which means 0.0004, which means 10 raised to 4 atm, which is really less pressure, that is at minimum pressure, the glow within the tube stops, but the gas continues to be conduct electricity. Glow stops. I told you there was a glow and there is a conducting of the electricity also. But when again I decrease the pressure, the glow of that particular one is stopped. But what happens? The pressure, the gas is started to conducting the electricity. So the glow surrounding the cathode or the negative electrode detach itself, leaving a space between it and the electrode. That is particularly called as Crookes dark space. Okay, Crookes dark space. Clear? What is this experiment, ma'am? What is this experiment, ma'am? It is a discharge tube experiment for the discovery of the electrons. Okay. So what happens means, as I told you, when the pressure is reduced into 0.01, that is approximately equal to 10 raised to, I told you that much less value, 10 raised to minus 3 to 10 raised to minus 4. What happens? There is an emission of color light stops, and what happens is the discharge tube started to glow within a faint greenish light. And this greenish light, they are actually coming from where, children? They are actually coming from the cathode. That invisible rays, that particular, this is because why that particular greenish light was there? It is due to the striking of the glass tube by some invisible rays coming from the cathode. So there was when the temperature was very less, I mean not temperature, children, pressure was very less, what happens? The emission or the electricity conduction of the gas was there. Initially we had a discharge tube. In the discharge tube you have the gas. That gas was conducting electricity. So when the minimum temperature, minimum pressure, it is approximately 0.001 mm of Hg, what happens? The emission of the color light stops. But there is the discharge tube started to form, or they started to glow within another color, which is a greenish light. That greenish light, do you know what? That is actually comes from the invisible rays. That is actually due to the particular striking of the glass tube by some invisible ray which is rising from the cathode. So whenever this particular pressure decreases, the glow within that is decreased and there is no glow, but the gas which is filled in that particular tube is actually moving, conducting the electricity. There is a greenish color. That greenish color is due to the some invisible rays. We don't know what is that invisible rays. The experiment told that some invisible rays which is from the cathode is actually striking to the glass tube. So that is because of that only the greenish light is there. So these rays are actually called as your cathode rays, and these rays are found to consist of negatively, negatively charged material which is called as the electron. So this is all about the electrons. Are you getting my point, children? So whatever happens at low pressure, when it is particular discharge tube, there is a two category, which is electrodes. Two electrodes are there, and there was a high voltage also. Whenever we give the high voltage, the pressure at low pressure, we started to reduce the pressure. First it was 1 atm, there was nothing happened to the gas, and the any lighting or nothing happened. Whenever we decrease the pressure towards 10 raised to minus 3 to 10 raised to minus 4, what happens? The flow of this particular light, I mean the flow of the gas, or the conduction of the electricity of the gas happens. And after we decrease the pressure, the conduction of the electricity and the conduction of the gas, electricity, the gas is conduct the electricity, that is happening, but the light is decreased. But after a few, when it was almost 0.001 mm of hg pressure, there is a striking, or there is a the discharge tube start to be glow with a greenish light. So that greenish light is basically, there are some rays, or there are some invisible rays is coming from the cathode. It's because of that rays only the greenish light is coming. So okay, the greenish light is coming, so there is some rays are coming from the cathode. Those rays are called as cathode, and it is coming from the cathode. I mean, since it is coming from the cathode portion, we can easily say that they are called to be electrons, which is negatively charged. Clear, everyone? Clear? Clear? This is all about the cathode. That is actually the discovery of the electrons. Cathode ray experiment. Clear? Good evening, Miss Ram. Clear? Shall we move to the next one, children? Shall we move to the next one? Now comes the properties of the cathode ray. Just note it down. Just note it down. This is going to be travel in a straight line and produce mechanical effects also. They will be producing mechanical effect. And what happens means, when the stream of the cathode ray, they will be. See, for example, this cathode ray. This is the cathode ray that is going to the towards the anode. So when we introduce, or we can say that when when an electric effect is applied to this particular stream, what happens means, they will deflect in such a way that towards the positive direction. So the particular electric field will deflect into the positive direction, means I can say that something negative is going on. That's how they have to find out, okay, there is something negative, and that's how they indicate that, okay, there's the cathode ray themselves is negatively charged. Clear, everyone? Clear? Clear? So this is how they find it out, this particular cathode ray. Clear? Perfect? Cathode ray that is actually negatively charged. And one more thing is, your children, so when there is a magnetic field also, so this is your flow of the particular cathode ray, this is your flow of the particular cathode ray, and we are introducing a magnetic field which is perpendicular to this flow. Okay, we are introducing a magnetic field which is perpendicular to this particular cathode ray. So what happens means, they deflected the direction expected for the negative particles. However, the negative particles has to be deflected. They deflected like that. So they from these conclusion, they got to know that, okay, the cathode rays are negatively charged. They are negative charge. They do have the negative particles. Clear, everyone? Clear? And the direction of the deflection shows the cathode ray are negatively charged. When cathode ray are allowed to strike a thin metal foils, it get heated up also. These are the properties which they got to know from that. Clear, everyone? Those who are watching, is it clear, everyone? Clear? Now there is a determination of the E by M. E by M is charge to mass ratio. E by M means charge to mass ratio. Okay. E by M, there is some points which you have to get an idea about it. I will tell that during the anode also. So there is something which is called as E by M ratios. It was J.J. Thomson which is determined the E by M ratio of the electron by measuring this particular deflections. Now, so what happens means, we can say that this E by M ratio is basically that is actually there are some properties. See, E by M ratio is not, it is constant for the cathode. Okay, it is constant for the cathode irrespective of the gas we are taken. Whatever the gas we can take in that particular discharge tube, but irrespective of that gas taken, the E by M ratio is going to be constant. Clear? Clear? That's fine. That's fine. Okay, E by M ratio. So determination of the E by M ratio of the electrons is done by the, one second, I will give that particular, it's done by the Millikan drop experiment. So what happens means, as the Millikan drops experiments, they got a value of E is equal to 1.602 into 10 to the power of minus 19. They do know the E by M ratio also. E by M ratio is 1.76 into 10 to the power of 8 Coulomb per gram. This is E is the particular charge, which is the coulomb and the gram. Now we got this value also, na? So why now we can, and we are just dividing this particular E by M is equal to, we can get the mass. Mass is going to be 9.1 into 10 raised to minus 8. Okay, so E by M ratio is constant. There is another point also, we have to note it down here. E by M ratio, that is going to be constant. Okay, that is going to be ratio is constant. E by M ratio is constant irrespective of the gas. E by M ratio is constant. Clear everyone? Okay. Next one is the anode or canard rays, which was discovered by the Goldstone. What will be the anode rays are the one, see, if the cathode rays are the one which is emitted from the cathode to the anode, which is negatively charged, which is the discovery of the electrons, means anode rays is going to be what? It is coming from the positively charged, right? Same thing is going to happen. It will be coming from the positively charged, they will be hitting. So they got to know that when there is a, as I told, everything is same only for the anode also. So what happens here is only the change is at low pressure only. Only the change here is, so whenever there is a, as I told you, from the anode, they will be getting the particular rays will be coming, and as a result of this, all these experiments, same thing will be happening. The thing, when there is a when they introduce a magnetic field also, which is perpendicular to this cathode ray, I mean anode ray, just like in the cathode, they here also they are introducing a magnetic field which is perpendicular to this particular one. What happens? They deflect it in a such a way that they have to deflect it for the positive deviation. I mean positively charged, just like how they will be deflected to the positive charge, they deflected it like that. And now there is a change in the E by M ratio here. This is like E by M ratio is not constant for the anions. I mean anode rays, it's basically depends upon the gas which we are taking. It is basically depends upon the what is the gas we are taking. Okay, so the gas which we are taking is basically, it depends upon the E by M ratio. Clear everyone? So we can say that in the cathode it was actually constant, and the anode it is depends upon the charge. For example, instead of hydrogen, I'm taking you, for example, if you have the helium, okay, instead of hydrogen, I'm taking you helium is the gas. Okay, so you can understand that here, for example, if I'm taking you H plus plus 1 electrons, He is equal to He plus plus 1 electron. Okay, so what happens here is E by M ratio means when the mass increases, E by M ratio has to be decreased, right? E by M ratio has been decreased. So you can see that H plus is going to have more E by M ratio than the He. Why? Because the hydrogen is having the less mass. Am I correct? Hydrogen is going to have the less mass. As per the atomic mass also, hydrogen is going to have less mass when compared to the helium. So what happens? Hydrogen is having the less mass, means what is going to be happening? E by M ratio as a whole, it's going to be high. So E by M ratio for the anode, we have to say that it's actually remains according to the particular gas we are using. Okay, clear everyone? Clear? Okay, so that is all about the anode also. I hope it's clear. Clear. E by M ratio also we discussed about it. Now comes the earlier atomic models, earlier atom models, what we are doing. Okay, first one was the Thomson model of atoms. J.J. Thomson, he was the first one who understand a particular atom, who gives some explanation for the atom. So what happens means here he says that the atom is considered as a sphere. Okay, he's considering atom as a sphere, just like the, for example, we can say that it is considered, say, in the straight structure of the watermelon, or we can say that plum pudding model and all, na? Just like that. So what happens means we can say that it is considered as a sphere which is having the negative charge and the positive charge, which will like it's a, the red portions are there now. It is just like that. I have the picture of it. 1 second. Yes. See, the atom is a consists of a sphere of positively charged. They do have the positive charge, and the negative charges are just embedded in that positive charge. He told that the atom is a sphere when it is a sphere of positive charges, and the negative charge, which is electrons, that are going to be embedded in it. Atom is a consist of the sphere of positive charges, and the electrons are uniformly embedded in this, or uniformly distributed in the particular atom. And this is a very important point which is actually true till now, right? Atom is electrically neutral. Whatever is the charge or whatever is the positive charge which we have, that is going to be having for the negative also. In that case, we can say that, or the number of the protons and the number of the electrons is equal. In that case, we can say that the atom is electrically neutral. What is it? Atom is electrically neutral. Therefore, this atom model is also called as the plum pudding model or watermelon model. You know about this, right? Watermelon model means, I can say that when we cut the watermelon, that red color is there, na? Red color which will which is eating, which is edible portion. That red color is actually your positive charge, and that non-edible portion is there, na? That seeds. Those seeds are your negative charge. So we can say like that also for the plum pudding model. Okay, or else we can also say that in the, I mean, watermelon also, but in the plum pudding model means we can say that small spices is there, which is nuts and fruits of that particular plum cake. That is basically your electrons, and the whole cake is there, na, that stuffed one, that is basically your protons. I mean, that is basically your positive charge. So the atom is actually considered as a sphere, which is the sphere of the positive charge, and the electrons is uniformly distributed in it, and they will be distributed in such a way that how they will be distributed, they will be uniformly distributed in such a way that they do have what, children? They will be electrically neutral, and that is basically called as a plum pudding model, which we studied. See, this is a plum pudding model, or this is the atomic model, where the particular these are all considered as the positive one, and those small that edible, that seeds, and those small ones, now that is basically called as the positive one. Clear, everyone? Clear? Okay, okay. Now comes the Thomson. The same here in the electron, this particular watermelon also. All this red edible portion is positive charge, and the small one, that is non-edible seeds, is called as the negatively charged. Clear, everyone? Now comes the Rutherford alpha scattering experiment. So firstly, it was considered by the J.J. Thomson. In J.J. Thomson was not able to explain a lot of things about it. It was just a it was not an experimentally determined one and all. He just told it, okay, the atom is going to be a spherical one, and there is a positively embedded one, and there is a charge of negative also, which is going to be equal, and as this atom is going to be electrically neutral. So he is not having experimental background or experimental support for this particular assumption. So now comes the Rutherford alpha scattering experiments, which was the very foremost, or we can say that, which was a very important experiment for leading for the atomic model concept. Okay, so what he done is, he done the alpha scattering experiment by using a gold foil. So he took the gold foil, which is thin layer of the gold foil, and he done it to see, in order to find out the arrangement of the electrons and the protons. So the Rutherford conducted the alpha scattering experiment. So what happens means, there is a source of alpha particles, and he make this particular alpha particle beams, that is to pass to the lead plate, and after that, when it is particular alpha particles are, alpha particles are positive charge. So when the alpha particles are coming and when they hit on the gold foil, they scattered. Okay, so when he checked the particular rays, or when as a result of this, when he checked the rays, there was some common things among the rays. There were some common things among the rays. Okay, so what happens here is, one second, the Rutherford bombarded a thin gold foil with a stream of fast moving positively charged alpha particles. Okay, and what happens, that movable circular screen which I have shown you now, that is coated with the zinc sulfate, that zinc sulfate, ZNS, okay, that was placed at the back of the gold foil, and that alpha particles, when they pass through that, when he took that particular one, and when he see the particular conclusion, he got to know that there is the most of the alpha particles are they passes through without any problem. There was no problem for the particles, alpha particles to pass. They completely pass it without making any problem. But there were some alpha particles which will having a deviation. There was some the kind of deviation which making a small angle. Okay, for example, I can say that when they are passing like this, they passed, when they reach somewhere, they made a complete, I mean, they made a small angle, they made some deviation, or they just scattered by making a small deviation or small angles. Okay, now very few out of very few, 1 out of 10,000 and all, what happens, they completely bounce back. So these are the three explanations, or these are the three conclusions, or these are the three findings he done it. So he got it. Like we can say that most of the alpha scattering or most of the alpha scattered rays are went without any problem. So we can say that okay, they went without any problem means there is no obstacles. Most of the place in an atom or most of the space in an atom is empty, right? Yes, and very few we can say that they made a small angle, which means they deflected which by making a small angle, which means they deflected by making a small angle. So you can say that okay, since the positive charge has to be deflected means there are something also in that. And very few, that is 1 out of 10,000, we can say that very few one get completely bounce back. Completely bounce back, what is it, children? Completely bounce back means we can go, it is going here and it's completely coming back to the same position. I mean, it's going and touching the particular one and it coming back, bouncing back. So very few alpha particle bounce back. So these are the 3 findings. From these 3 findings, he got to know that okay, since so most of the alpha particles has passed without any problem, it indicates most of the space in the atom is empty. What does it indicate? Most of the space in the atom is empty. Empty. Okay, next one is alpha particles. Since alpha particles, I told you it's a positively charged, so we can say that it's a positively charged and having considerable mass, could be deflected only by some heavy positive charged center. So if they are deflecting, there should something which is like positive light terms or light charges is going to be deflect, am I right? So they do have some charge, they do have some mass, they do have positively charged. So if it is has to deflected, or when they hit this particular another big positive mass only, they will be deflecting, or they won't be deflecting. So mostly all the particles are going in a straight line. Only very few that they hit and they deflected means I can say that which is a positively alpha particle which do have some mass, they are hitting and they are deflecting means the hitted one should have more mass and they should be the positive charge also, right? So they got to know that okay, there are some heavy positively charged which is having a mass also in the center. Okay, clear? And now small angle of deflection of alpha particle indicate the presence of the heavy positive charge in the center of the atom, which I told you. And the Rutherford named this particular mass or this particular center of the atom as nucleus. And the nucleus will be having the particular, now you know that nucleus is going to have protons which is positively charged. That is the reason why the positively charged alpha particle got deflected. Are you getting my point? That is that is the reason why the positively charged alpha particle got deflected. A few of the alpha particles are bounced back due to the direct following with the direct collision with the nucleus. This, since it is having a complete collision, they are just coming back. Clear everyone? Okay, so this is what happens. Mostly all the particles which is going to be here and all, they are going without any problem. It's very few when it is comes nearer to this particular this portion, not towards the center, this portion along this where the effect of this nucleus is there, they come and they make an angle and they went, they deflected. Very few they come in and they join the center and they deflected back. So this is something which is the result of this alpha scattering experiment. So I can say that in the atom, the entire mass and the positively charged is concentrated in the particular very small center which is called as your nucleus. So nucleus is having a positively charged one. The magnitude of the positive charge on the nucleus, that is the number of protons, is different for different atoms. You know that every atoms will be different. If you take another atom, instead of gold foil, if you take something else, they will be having different one. Clear everyone? Okay, the nucleus is surrounded by the negatively charged electrons, which is balance the positive charge. They do have the electrons also, and these electrons are not stationary, but they are in a revolving speed. They are actually moving. Okay, they are actually revolving around the nucleus in a certain speed. Clear? And most of the space, of course, the spaces of the atom is empty. So we can say that this is going to be a nucleus, and the nucleus is going to have the protons and the neutrons. They do have the protons and the neutrons at the center of the atom. See, this is at the center of the atom. We have the nucleus. In the nucleus, we have the protons and neutrons, and the particular electrons are revolving around in a fixed path or in a fixed way or path. They are revolving. So this is basically the Rutherford atomic orbitals or atomic model. There are a lot of there is a lot of demerits for this. They were initially they were accepted, but after a while they was not able to accepted it because of a lot of cons. The pros and cons are there because of a lot of demerits, which was just not accepted anymore. Okay, now that is also called your planetary model of atom. You can understand that because the planet is basically, we can say that nucleus is like around the, nucleus is actually the sun, and the particular electrons are surrounding the sun, means I can say that that is nucleus is the sun, and the particular planets is considered as the electrons. So we can also call it as planetary model or planetary electrons. Clear everyone? Now comes the atomic number. So what do you mean by the atomic number? So you can say that the atomic number, I told you in the some basic concept also. So atomic number is there, you have the mass number is there, you have the isoelectronic species, isotopes and isobars, which are very important. Okay. So atomic number is the number of the positive charge carried by a nucleus of an atom. For example, in an atom or in an element, we can say that it is the number of the positive charge which is there in the particular nucleus of the atom. That is particularly called as the atomic number. So number of protons, and you know that electrically the atom is equal. Am I right? Or electrically the atom is neutral. When the electrically the atom is neutral means I can say that the number of the protons and the number of the electrons is going to be equal. Clear everyone? Clear? The number of the protons and the number of the electrons is going to be equal in the atom. Clear? It's going to be equal in the atom. So I can say that the number of the proton is going to be equal to the number of the electrons in an atom. Okay, fine. Yes, perfect. Now, discovery of the neutrons. Neutrons was discovered by the Chadwick, which is 1932. So we have the neutrons next one. Neutrons was, it is actually the beryllium is there now. When he discussed the beryllium, when they bombarded with the alpha particle, when the emitted radiation is consist of a new particle. There was when it get heated with this particular alpha particle, which is He24. When they just heated with this helium particle, alpha particle, that is basically what happens. There is a formation, or the emitted radiation also comes with a something which is called as the neutrons also, which is no charge. No, there is no charge. They do have a mass, but they don't have any charge. So this particular chart we called the particular one particle as neutron. Clear everyone? So neutron is a subatomic particles which has mass equal to that of hydrogen atom, which is actually and carrying no electric charge. They don't have the charge, but they do have the particular mass which is equal to hydrogen, which is 1.675 into 10 to the power of minus 24 grams. Now comes the mass number. Mass number, so I told you the atomic number is something which is the number of the protons and number of the electrons. So number of the protons and the electrons in an atom is equal. So I can say that is something which is comes under the category of the atomic number, right? We discussed about it. How much of the, when the nucleus, how much number of, or how much particle, how much number of electrons or protons are there in the particular nucleus. That is something called as the atomic number, which we can consider as the number of protons or number of electrons also, because since an atom is electrically neutral, it can be considered as a proton and the electrons, or the electrons. Now come the mass number. Mass number is something which is the mass number of an atom is mainly due to the protons and the neutrons. So nucleus, I told you, nucleus is consist of the protons and the neutrons. Protons plus neutrons, right? So what happens means they collectively called as the nucleus. They collectively called as the nucleons. So we can say that the protons and the neutrons, in that I can say the total number of the protons and the neutrons in the nucleus. How many protons are there? How many neutrons are there? So protons charge is basically 0. Okay. They don't have any charge, but they do have the number. So we can say that the number of the protons and the neutrons is called as the mass number, and which is denoted by the A. Atomic number is denoted by the Z. Okay, clear? So the mass number is the number of protons plus number of neutrons. You can easily find it out when you got the atomic number. Atomic number is something here we can find it out. This is your atomic number. Atomic number. So number of neutrons is equal to mass number minus atomic number, A minus Z. So atomic, see, number of neutrons, if we want to take, we can minus it. Mass number minus atomic number. Clear everyone? Okay. Now comes the isotopes. Isotopes are the one which will be having atoms of an element. Okay, the atoms of an element, they will be having atoms of an element, for example carbon itself, atoms of an element, they will be having atomic numbers same. They do have the, we will be writing the atomic number like this, right? This is X is an element, we write the atomic number here and the mass number here, Za. So this is going to be same, that is atomic number is going to be same, which means number of electrons is going to be same, which is atomic number, which is the number of electrons or protons in an atom is going to be same. But they do have some change in the mass number. So particularly when the number of electrons are same means I can say that when the number of electrons or number of protons are same means I can see that mass number changes, they are same and the mass number is difference means I can say that there is a change in the number of the neutrons. Because see, whenever there is this particular Z, which is atomic number, which is the number of the proton, same means in the mass number we can say that it is a adding of proton plus neutron, right? It is the addition of protons plus neutrons. Yes, so when the protons are same means there is a change of what? Neutrons only. So we can say that mass number is of an element is there is different neutrons, number of neutrons, or else I can say that same atomic number or same number of protons. For example, hydrogen has 3 isotopes, that is first one is the protium, deuterium, okay, and tritium. So I can say that protium, deuterium and tritium. So this is going to be the particular isotopes of the hydrogen. Everyone is going to have the atomic number 1 and this protium is going to have the neutron number 0. 1 minus 1 is going to be 0. And next one is carbon has 3 isotopes, which is carbon 12, carbon 13 and carbon 14. Next one is the isobars. So you can say that if isotopes are the one which is having the down portion, which is your atomic number, atomic number are same means I can say that mass number, isobars are the one which will be top number, which is going to be the mass number. Mass number is going to be the mass number will be the same, the mass number, they will be having same mass number. We can say that, for example, you have Z, you have the atomic number Z, X, I will take 1 second. X, Z, A. Okay, this is going to be the atomic number, this is going to be the mass number. This is going to be different. One second. This is going to be same, not different, children, same, which means mass number is going to be same. This is going to be different. Okay, the atomic number is going to be, for example, argon, potassium, calciums are equal. Argon is do have the atomic number as 18, potassium is 19, calcium is 20, but they do have the mass number what? 20. Clear? They do have the mass number 20. That is particularly the isobars. Clear? So isobars are the one which will be having the top portion same. We can say that the upper portion or middle portion, lower portion will be different. Upper portion is same, which means I can say the mass number is going to be same, 20 for 40 for everything, argon, potassium and calcium. But when they consider about the atomic number, which means argon is going to be having 18, potassium is 19, calcium is going to be 20. Clear, everyone? Okay, and carbon is nitrogen also. Carbon is for 12, carbon atomic number is 6 and nitrogen is 7, but they do have different same mass number. Now comes the isotones. Isotones are the one which will be having same number of neutrons but different mass number. Mass number will be different. They do have mass number different, but so neutrons number is same. But neutrons number is same. For example, silicon, phosphorus and sulfur. So here everyone is having different number of this particular mass number also. Mass number is also different. They do have the atomic number is also different. But when we considered about the number of the neutrons can be considered as 30 minus 14. Am I right? Here 31 minus 15. Here 32 minus 16. Right? So I can say that they do have the different number of atomic number and mass number, correct? They do have the atomic number and mass number different, but same number of the neutrons. Here 30 minus 40 means it's going to be 16. So that is going to be 31 minus 15 also, 32 minus 16 also. Clear, everyone? Clear? So these are the things which you have to keep in your mind. Okay. Now, nature of the electromagnetic radiation. Now comes the chapter which is really important. electromagnetic radiation. So what is electromagnetic radiation? What is the characteristics of the electromagnetic radiation? What is the characteristics of the waves? All those things we are going to discuss. Just have a look on whatever we studied till this is a separate portion. Okay, this is about the mass, isotopes. One more thing, children, you have to get an idea about one more thing here, which I forgot to tell you. Isoelectronic species. We didn't discuss that. Electronic species. Isoelectronic species are the species which will be having same number for the same number of electrons. Species which have same number of electrons. Species which have same number of electrons are called as the isoelectronic species. For example, you have this oxygen is going to have the carbon, nitrogen, oxygen, right? Carbon, one second. For example, nitrogen and oxygen. In the nitrogen, they do have the atomic number is 7. Oxygen is going to be 8. For example, if I'm telling you 2 minus, which means it is going to be 10 electrons. Here it is going to be 7, which means I can say that 3 minus, N3 minus or F minus. So what happens? Nitrogen, the atomic number is 7 only, right? 7 only. But the number of electrons is going to be 7 plus 3, which is going to be 10. Here the oxygen is going to be the atomic number 8, right? Atomic number is 8. Correct. So what happens here is the number of electrons is going to be 8 plus 2, 10. Here fluorine is having the 9 and the atomic number is going to be, if it is accept 1, what happens? Number of electrons is going to be 10. Clear? So they do comes under the category of the isoelectronic species. Clear, everyone? For example, Mg2 plus also comes under this category, or else I can say that Na plus also comes under this category. Mg2 plus also. Na plus is having total number of electrons 11. When they give 1 electrons, they are going to have the 10 electrons. They are also an example. Mg2 plus will be having, they do have 12, right? When they give 2 electrons means it is going to be 10. Clear? Okay, so now comes our electromagnetic radiation and characteristics of the waves. So please do have a look on whatever we studied so far. Please do have a look on the things which we have studied so far. Just read it one time, children, so that we can take the next topic, electromagnetic radiation, and what are the things comes under that category. All those things we have to take now. Shall we do? So what happens here is when the Maxwell theory we are going to approach into. Maxwell say that the light is actually travels, it propagates or travel through the space through the in the form of the waves. So you know the waves, right? They are in the form of the waves. They are in the form of the waves, light. And that particular light, that particular wave, since it is in the form of the waves, means we can say that that waves are actually associated with this that electronic and magnetic field. Okay, that waves are actually in the associated with electronic and magnetic field. And these, are you able to see me, children? Everything is fine from my part? Okay. And therefore these waves are called as electromagnetic waves, or just like Maxwell told that okay, the light is travel when it is through a medium or in a space, we can say that they are in the form of waves, and light there does not need a medium to travel. Okay, so they are in the form of the waves. And of course we can say that the wave is actually associated with the electric and magnetic field. They do have some difference when they come in contact with the electric and magnetic field. That is something which is associated, which is meant by association. There will be some change, and therefore those waves are called as the electromagnetic waves or electromagnetic radiation. The radiation which is emitted by the waves when, or emitted by the light when they travel through a space in the form of the waves, we can say that. Clear? Clear? Okay, so now comes the what are the characteristics, means as I told you, the electromagnetic radiations propagate through the space in the form of the waves, and they require, this is really important, no medium for the transmission, and they travels with the velocity of the light, 3 into 10 raised to minus 8. So they will be traveling on the velocity of the light, and the energy of the electromagnetic radiation is directly proportional. This is really important. Energy is directly proportional to the its frequency. We will learn about this frequency and wavelength, everything. The energy, as of now, just understand that energy is directly proportional to the frequency. Okay, inversely proportional to the wavelength. It is directly proportional. We will write this. Okay, we will write this and we will come to some conclusions and all from this. So energy of that particular electromagnetic radiation, that is directly proportional to the frequency. It will be directly proportional to the frequency. And now you may then, what is frequency, what is this wavelength, and what is this wave number, everything we will discuss in this. Okay, so as of now, energy is directly proportional to the frequency. It's inversely proportional to the wavelength. Okay, so these are the particular properties of the particular electromagnetic radiation. It was on the form of the waves, and they do have some deflection, or they will be showing, it will be associated with the electric and magnetic field. They will be having some changes according to that. And there is another more point, which is like, what is the next point, children? This particular all electromagnetic radiation travels with the velocity of light. And one more thing, they do not require any medium of transmission. And one more very important thing is directly proportional to the frequency. Electromagnetic, the energy is directly proportional to the frequency and inversely proportional to the wavelength. Clear? Clear? Hi, good evening, Pawan. Clear? So I can say that the characteristics of a wave, when we are telling you this is a wave, we can say that this is your crust and this is your trough, right? You know this about it. So amplitude is something with the height of the wave, we can say that. A height of the wave which includes your crust and curve. Crust and trough, and crust and trough. Now from the wavelength is basically one crust to the another one crust to the another crust, or else I can say that one trough to the another trough also. That is also called as the wavelength. Okay, so these are the few things which you have to understand. Wavelength is something which is from one crust to another crust, or one trough to another trough, and amplitude is basically the height. Clear, everyone? Clear? Yes, Pavan. Good evening, Pavan. Now comes the wavelength, which is denoted as lambda. Okay, it is denoted as lambda. The distance between, as I told you, the distance between two adjacent crest or trough. One second. Two adjacent crest or trough is called as the adjacent crests or troughs as called as wavelength. It is denoted as lambda, and it is expressed in the terms of the terms of Armstrong units, A naught Armstrong unit, which is equal to 10 raised to minus 10 meter and 10 raised to minus 8 centimeter. This is required, children. They will ask you some question which may in the final stage they will ask you at the wavelength in centimeter or wavelength in meter. So whatever wavelength we are getting, we have to convert into centimeter and meter. So usually the wavelength in Armstrong is equal to 10 raised to minus 10 meter or 10 raised to minus 8 centimeter. Clear, everyone? Okay. Now comes the frequency, mu. Frequency is equal to, it's written as mu, or nu. Somewhere mu, somewhere nu. No, this was okay. Frequency is basically, I can say that it is the number of the waves which is passing through a per point or given point in 1 second. We are giving a 1 second of time, and that frequency is basically how many waves can pass us through that particular point in a given second of time. In a 1 second, here's a 1 second of time, I'm giving you 1 second of time. In that 1 second of time, how many waves can be passed us through that particular given point? That is the frequency, which is called as nu. So the frequency's unit is actually hertz. So the units is actually hertz. It's usually given in the hertz. Okay, 1 hertz is equal to 1 cycle or 1 second. So 1 cycle per second. In 1 second, you can get 1 circle. 1 cycle, not circle, cycle. Okay. So I can say that frequency is something, it is the number of the waves which is passing through a point in a second. In a given point in a second. That is something called, in 1 second is called as the particular frequency. Now comes something which is frequency is equal to, I have some equation here, children. Listen carefully to this. This is going to give you some basic grip on the chapter. Okay. So lambda is equal to c, frequency mu is equal to c by lambda. C is going to be the velocity of the light. Okay, c is the velocity of the light, and lambda is going to be the frequency. You got it. Frequency which we already discussed. 1 second. 1 second. I written as long. This is wavelength, children. Okay. So mu is equal to c by lambda. C is the velocity of the light, and lambda is the wavelength. So this is something, this is the equation which comes under the category of the frequency which is required for you when they ask the questions and all, which is required for you. Okay. Now comes the wave number. Wave number is something which we can say that this is denoted as like this. Frequency, that sign is there, na? We have to give a line for that. The number of waves passing per unit distance. In a unit distance, how many waves are passing. So for frequency is number of waves are passing through a point in 1 second. This particular wave number is something, number of waves are passing per unit distance. So wave number is equal to 1 by lambda. 1 by lambda is going to be your particular wavelength. So I can say that, see here we can give a equation. 1 second. I will just write it here. Okay. So lambda is equal to, mu is equal to c by lambda, where lambda is the frequency, and wave number is actually, it is 1 by, it is inverse to this. Okay, 1 by lambda. So this wave number is equal to 1 by lambda, means I can give this as c by lambda, which is equal to c into 1 by lambda is equal to wave number. So I can say that frequency is equal to c into wave number, which is frequency is equal to wavelength velocity of the light into wave number. Frequency is equal to velocity of the light into wave number. Frequency is equal to velocity of the light into wave number. Are you able to follow me, children? Wave frequency is equal to velocity of the light into wave number. This is also an equation which is, you have to get an idea. Okay. Next comes the velocity. Velocity means I can say that it is the distance which is traveled by a wave in 1 second, which is called as the velocity of the wave, and it is generally denoted by the letter c. Velocity of the wave. Okay. Since the light is actually considered as in the form of the wave, we are taking it as in the wave. Velocity of the light or velocity of the wave is also correct. Okay. Amplitude, it is the height of the crest or the depth of the trough of the wave. It is denoted as A. These are the things which you already know. Wave number, they already given it to you. See, wave number is equal to, it is defined as the number of the wavelength per unit length. This is already discussed now only. Yes, Soumya Pal. Good evening. And it is the inverse of the wavelength, which means I can say that it is the inverse, means mu, this mu bar is equal to 1 by lambda, which is mu is equal to mu, that is frequency is equal to c by velocity of the light or velocity of the wave divided by lambda. So I can say that c by lambda is going to be c into mu, right? Velocity of the wave into wave number. Clear, everyone? Clear? Okay. Now relationship between the wavelength, frequency and velocity. We can say that the velocity is equal to wavelength into frequency. Wavelength into frequency. Velocity is equal to wavelength into, that is nothing. Mu is equal to lambda, c by lambda, I told you, na? Mu is equal to c by lambda. So where C is going to be lambda mu into lambda, which means mu means the frequency and lambda is going to be the wavelength. The same thing only, which I already told you. This is all things we already told you. And the velocity of the electromagnetic radiation is going to be 3 into 10 to the power of 8, which is velocity of the light, 3 into 10 raised to minus 8. I mean 3 into 10 to the power of 8. Clear everyone? So this is from the lambda is equal to, mu is equal to C by lambda. Mu is the frequency is equal to C by 1 wavelength. From this, velocity of the light or velocity of the wave is equal to, we can multiply it, which is frequency into wavelength. This is the equation. Okay. Now comes the dual nature of the electromagnetic radiation. So what happens here is, the electromagnetic nature, they have one particle nature, they do have some nature, dual nature. Okay. Do you know any idea about it? What are the two natures of the electromagnetic radiation? Particle nature is also there, wave nature is also there. They do have two nature, which is particle nature and wave nature. Okay. So we have to discuss that. Just write down, just revise whatever we discussed as till now. So there is dual nature. Are done? The wave is having dual nature, which is particle nature, and you have the particular wave nature. In the wave nature, Hare, hardly peru ma'am, if an electron of it. It depends upon the thickness of the wall. What a doubt. Okay, fine. So there is a dual nature of the wave, that is particle nature, and also you have this particular wave nature. In the wave nature, you have the interference, diffractions and all those things. In the wave nature, we are not going to study that. So I can say that the wave, they do have dual nature, which is particle nature. They do have the wave nature and particle nature. You have the wave nature and the particle nature. Wave nature, we are going to study about the interference, diffractions and all. That is not, interference and diffraction is not going to discuss in the wave nature. We will be discussing about the black body radiation and photoelectric effect. We will be discussing about the black body radiation and photoelectric effect. Photoelectric effect. There are two types in the black body radiation and photoelectric effect in this particular particle nature. In the wave nature, as I told you, you have the interference and you have the diffraction. We are not going to discuss about these two. Okay, we are not going to discuss about these two. We do discuss about these things. Okay, clear everyone? Black body radiation and photoelectric effect. Clear? We have a lot of things to discuss. I really don't know how to discuss all those things. Now comes the black body radiation. Black body radiation is basically, we can say that it's a body which will be emitting and which will be releasing also. It's like body which emits and absorbs all the frequency in the all the frequency is known as the particular black body. They will absorb also, they will give also. If we are telling, like, we can say that they will emit, and they will absorb and they will emit also, like this. This is basically, they are absorbing and they are emitting also. That is something comes under the category of the black body radiation. The radiation emitted by the black body is called as the black body radiation. They will be emitting and they will be giving also. That is something comes under the category of the black body radiation. Now photoelectric effect is basically what happens means, when a particular light, okay, when a particular light of the suitable frequency, or suitable, we can say that when the suitable frequency, what happens means, suitable frequency frequency when they hit on a particular metal. There are some criteria for the metals also. When a particular frequency of the light is hit on the particular metal, frequency of light, certain frequency of the light is hit on the metal, what happens? The metal will be having the electrons. The electrons are going to ejected, okay, and this phenomena is known as the photoelectric effect, and the emitted electrons are called as photoelectrons. So whenever there is a frequency of the light is hit to a metal, as a result of this, the electrons from the metal is emitted. That particular effect or that particular one is called as the photoelectric effect, and we can say that the emitted electrons are called as the photoelectrons. Clear everyone? That is something comes under the category of the photoelectrons, which both will be comes under the category of the particle nature. Black body radiation also, photoelectric effect also. Black body radiation is the ideal body which can emit and which can give also, which can absorb also the radiation. Okay, that is something comes under the category of the black body radiation. Okay, now comes the photoelectric effect, means when a particular suitable frequency of the light is given to the metal is going to eject the electrons. That particular phenomena is basically called as the photoelectric effect, and the electrons are called as photoelectrons. Now some important aspects are there. As I told you, there are some criteria. The ejection of the electrons from the surface of the metal will take place only if the incident radiation has certain minimum frequency. See, what happens here is, when there is a frequency of light is hitting to the particular metal surface, okay, when there is a frequency of light is hitting to the metal surface, this is your metal surface, this is your metal surface, and there is electrons. So this electron has to be ejected. So this frequency of the light which is emitted, they have to be in a such a condition where they can emit the electrons. For example, if I'm telling you this electrons can be emitted only by 20 frequency, 20 mu, 20 frequency I'm telling you, okay. But when the emitting one is having a frequency of 10, means what happens? There is no chance of emission of these electrons is not be possible, right? So I can say that they should have certain minimum frequency. The particular emitting or the particular incident ray or incident radiation, that particular one which is striking to this particular electron should have some minimum frequency. Then only the minimum frequency of the light to cause this particular emission of the electrons is called as the threshold frequency. That is basically called as the threshold frequency. So is it all the frequencies of the light can emit the electrons? No. All the frequencies of the light cannot emit the electrons. No, that's not possible. They should have some frequency, or they should have the minimum frequency which has to be given to emit the electrons. Okay, that is basically called as your threshold frequency. That is basically called as your threshold weight frequency. And one more thing is that there are few points written. The kinetic energy of this ejected electrons is proportional to the frequency of the incident radiation. So what happens here is, I'll tell you here. So what happens here is, this is your metal surface, okay, this is your electron. So I'm giving a frequency of particular light here. So what happens, the electrons is going to be ejected. So the electrons will be going to ejected in a such a way that how much frequency of the light I'm giving you, right? For example, if I'm giving strong incident light, means that much will be the kinetic energy, that much fast it will be going. Kinetic energy means it's moving energy, right? So when I'm giving you high frequency of the light to the metal, or high frequency of the particular incident ray, which is your light, high frequency of incident radiation, what happens? That much kinetic energy is going to be ejected from the electrons, which means I can say that it is directly proportional. How much kinetic energy of an ejected electron is required, that is proportional to the how much frequency light you are giving. Am I right? How much frequency of the incident radiation, and independence of the intensity. How much intensity are not telling, how much frequency or how much is the frequency to the particular one. Clear? If no doubt, if an electron moves inside an atom, they do have the deflection to the magnetic and electric field. They do have the deflection. They will be showing something. Okay. Now, the number of the electrons ejected from the metal surface is proportional to the particular intensity. Now, intensity is depending upon how much electrons. See, basically, this is easy, children. Frequency is basically how long that electrons can go. That is the kinetic energy. Okay. How intensity we are going, giving to the particular incident rays, how much electrons can go. Okay, that is different. Frequency basically how long the electrons, or the kinetic energy of the emitted electrons, or I can say that the frequency is going to be, or the intensity is going to be how much electrons can emitted. That is something which is called as this particular one. Clear? 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 Okay, that is proportional to the intensity of the radiation. There will be some limitations for that early. You determine the compounds. By that means that is actually a property now. So uh, that is when, see, they will be showing some reflections only now. In that reflection we cannot come to a conclusion, right? Okay, so what is it? So kinetic energy of particular ejected electrons can be directly proportional to the how frequency we are giving, but intensity can be determined, or how much intensity of the incident ray is directly proportional to that much electrons, how many electrons are giving. Okay, that is the number of electrons ejected from the metal surface is proportional to the intensity. Clear, everyone? Now comes the Planck's quantum theory. So in order to explain this particular black body radiation, I told you they do have they will be emitting, they will be absorbing also. That is something comes under the category of black body radiation. And photoelectric effect means when they do get certain amount of the frequency of the light, the particular metal start to eject the electrons. That is that particular frequency of the light is directly proportional to the kinetic energy of this particular ejected electrons, and intensity of this particular incident rays is directly proportional to the how many electrons are ejecting, right? That is done by the quantum theory of radiation, that put forwards a new theory called, which is called as quantum theory, which is Planck quantum theory. Okay, so quantum theory is telling that the radiant energy which is emitted or absorbed not continuously or discontinuously, it is in the forms of the small packets. So what happens means, I told you the energy is there. Okay, the energy is the energy, which means when the electrons is emitted, the electrons are emitted in the form of the energy. So it's not in the continuous form of a waves or something, it's not like in the continuous forms of waves or something. We can say that it's continuous forms of what? It's a packets of small packets of energy, which is actually called as the photons, or which is actually the small packets of the energy is called as the quanta. Clear? So the radiant energy which is emitted or absorbed, whatever the energy or the waves which is emitted or absorbed, is directly proportional. That is not on the basis of the what? It's not on the continuous one. It's a discrete, which we count it small packets one, and that packet is actually called as a quanta. And we can say that each packet of this wave was associated with a definite amount of energy. That particular amount of the energy for a quanta is called as the photon. That is particularly called as the photons. Clear, everyone? Nuclear magnetic resonance. That can be done, but again there will be some problems, or else they would have done this for the formation of this particular ones and all. Okay, so what happens here is, quantum mechanics is basically, we can say that the electrons are, or the emission of this energy is not in the not in the continuous path. It is actually discontinuous path, which is actually small packets, which is actually called as a quanta. And this particular energy, that is a definite amount of the energy, is known as, in the case of the light, if it is the quanta, in the case of the light, the energy is known as the photon. Are you getting my point, children? Yes. Now comes the amount of the energy of the quanta. Amount of the energy quanta of the radiation is directly proportional to the, directly proportional to the frequency, which means I can say that E is equal to, this is the equation, children. E is equal to, this I will write it here. E is directly, energy is directly proportional to what? Frequency. Frequency is your mu. Now I'm giving a constant, which is your Planck constant, which is 6.626 into 10 to the power of minus 34. Okay, so H mu. So I can say that mu, this nu is equal to, which is C by lambda, right? C by lambda. So when I'm giving this value, which you can, HC by lambda is going to be the value of energy. This is really important. HC by lambda is going to be the energy of the value, energy of the particular, the amount of the energy of the particular quanta of radiation is equal to hc by lambda, where c is the velocity of the light or velocity of the wave, lambda is the particular wavelength. And I can also give in like this. This can be written as like integral multiple, we can say, right? E is equal to h mu. Clear, everyone? Clear? Or if it is an integral multiple, which means I can write it as h mu na. So which is E is equal to nh mu, where n is the 1, 2, 3 multiple, n is the number. Clear? Clear, everyone? Okay. Now comes the electromagnetic spectrum. Oh my god, we have a lot of things to complete. Okay, fine. Now comes the electromagnetic spectrum. Electromagnetic spectrum is something which is it is basically, we can say that it is the arrangement of the, different types of electromagnetic radiation according to their increasing in the wavelength, increasing or decreasing in their, increasing in the wavelength and decreasing. Since the wavelength increases means of course the frequency has to be decreased. There should be a decrease in the frequency. So I can say that this is going to be the value. So this is your visible light, this is the infrared, this is the microwaves, and this is the radio waves. Here you have it. One second. Okay, infrared, then UV rays, gamma rays, cosmic rays. You have between these two, you have the X-rays also. So this is the particular way. Visible light is the infrared, microwaves and radio waves, and you have this particular one. This is the increasing order of the frequency. Okay, frequency increasing order. So you can understand that E is equal to h by lambda. C by lambda is equal to hc by lambda. So when this particular wavelength increases, energy is going to be decreased. So I can say that here to here what happens, the wavelength increases, as a result of this energy is going to be decreases. Clear, everyone? Clear? Okay, clear. Now comes, you have the spectrum. You have the two types of the spectrum, children. You have the continuous spectrum and non-continuous spectrum. So we can say that in the particular spectrum, the spectrum are non-continuous spectrum. You can say that there are two types, which is emission spectrum and absorption spectrum. What are the two types, children? See, emission spectrum and absorption spectrum. In the emission spectrum, you have the continuous spectrum, okay, continuous spectrum and discontinuous spectrum. Continuous spectrum and discontinuous spectrum. Okay, children. It's what is the time now? 5:17 now. Come back by 5:20. Okay, 5:20. 3 minutes of break. Okay. Am I audible, children? കേൾക്കുന്നുണ്ടോ? I mean, are you able to hear me? This is actually, I talked in Malayalam, children. I'm so sorry for that. 1 second. Mm, The time came in the class. Fine. Mm. Am I audible, children? Please do tell me if I'm audible or not. Whether I'm audible or not. Audible? Audible? Yes. Perfect. I'm audible. Okay. So I told you we were discussing about this particular emission spectrum. Emission spectrum is actually, there is two types, which is continuous and discontinuous. In the continuous spectrum, this is basically where there won't be any gap in the color lines. Okay, there is no gaps in that. And discontinuous spectrum means there will be gap. So I can see that, for example, discontinuous spectrum we are going to discuss there will be some gaps, and that in that particular discontinuous spectrum you will be learning about the line spectrum and band spectrum. Line spectrum and your band spectrum. So color lines which is separated by the gap is called as the line spectrum. You can see that there is lines. So this is red, yellow, blue, green, right? Which is actually for the atoms, which is actually comes under the category of this particular line spectrum. Now band spectrum is something the color bands are separated by the dark gap. So they will be having a dark gap, and that will be the separation of this particular color gap. So you can see that, here you can see that there is a band, color bands are the red, yellow, blue, green. So they are actually separated by big dark gap. Okay, that is something comes under the category of the band spectrum. From you can say that it will be forming molecules, H2 molecules, an example. For example, the line spectrum, it is hydrogen is an example. So these are the two different types of spectrum which is comes under the category of the discontinuous spectrum. In that, a spectrum which you have the particular hydrogen spectrum of hydrogen atom. So spectrum of hydrogen atom is basically, it is obtained by an electric discharge through the hydrogen gas taken place, and it should be, as I told you in the particular experiment of cathode and anode, now it should be done in the low pressure, and this light emitted is analyzed in the using the spectroscope, and that particular one will be having different regions of this, different regions was appearing. So first one, it was like some of the lines are found in the visible regions, and others all are found in the ultraviolet and infrared region. The different series are Lehman series, Balmer series, Paschen series, bracket and Hund. What are the different series? Lehman, Balmer, Paschen, bracket and Hund. Lehman series is approached near to the ultraviolet region. Balmer series is approached into the visible region. Paschen, bracket and Hund appears in the infrared region. So these are the one when we consider the hydrogen spectrum, and when we take that particular light which is emitted from that and analyzed by using the spectroscopy. So this is all about, okay, before what is happening in the Lehman Balmer series and all, we have to further go for the Rydberg equation. Okay, Rydberg equation gave a general expression giving applicable to all series of lines in the hydrogen spectrum, which is 1 by lambda, which is a wavelength, is equal to RH, which is a Raymond constant, into 1 by N1 square. I'll tell you what is this N1 square, minus 1 by N2 square. So basically that is like, which is the value of this particular R is a Rydberg constant, which is 108 109,677. So this is particularly 1 by 1 n1 raised to n1 squared minus 1 by n2 square. Alright, what is this exactly? Listen carefully. So this is basically your hydrogen spectrum. You can say that n is equal to 1 means it's Lehman. You will be having n is equal to 2 Balmer, n is equal to 3 Paschen, 4 means bracket, and 5 means Hund. Okay, so that is number they are telling, the number of the particular ones. Okay, now n is equal to 1, 2, 3, 4. So when the Lehman series, it is going to be n is equal to 1, which means n2 is going to be 2, 3, 4, 5, 6. Anything can be. So I can say that here it is n1 is going to be 1, n2 can't be anything. For the Lehman series, n1 is going to be 1, but n2 can be anything. So same as that for the particular Balmer series also, because n1 is, it started from the n is equal to 2. Am I correct? Clear? Okay. Then n2 is equal to 3, 4, 5, 6, 7. Okay. Now, Pooja Prajapati ma'am, regular class hote hai kya? Regular class won't be there, but we will be weekly, we will be giving the classes, if I'm not wrong. Okay. Next one is the brackets passion series, which is n1 is equal to 3, n2 is going to be 4, 5, 6 and 7. n1 is equal to 4, which is going to be n2 is going to be 5, 6 and 7. Clear? So that like that how we can find out the Rayburn formula, which is for the wavelength 1 by lambda. Okay. Now coming to the how the Rutherford, we discussed about the Rutherford only now, then we have to go for this particular one. Rutherford, what are the particular failures? First failures was to explain this particular stability of the atoms, how the stability of the atoms comes, how they are stable, what are the conditions, all those things he was not explained, he was not possible to explain it. Next one, he failed to explain the existence of the particular hydrogen spectrum. They didn't explain anything about the lines in the hydrogen spectrum. He was not able to, it was all about the hydrogen spectrum. He was not able to find, or he was not able to explain anything about the spectrum. Okay, that was another drawback. And another important one is the, for example, by the Maxwell theory, we can say that according to Maxwell theory, a charged particle, when they emits and they accelerate and they emit the charges in the form of the electromagnetic radiation. So what happens means, when it means that like so as per the Maxwell theory, whenever there is a emitted charge or accelerated emits energy in the form of the particular electromagnetic radiation, the particular particle. Okay, so that is according to the Maxwell theory. Now what happens means, according to Rutherford theory, the electrons are just revolving around the nucleus. That's true. So what happens means, the electrons also will be, since whenever there is an electrons are they are actually in the particular acceleration, so whenever they are accelerated, they will be emitted the energy, the particles will be emitted the energy also. Since the electrons are surrounded, the electrons are also revolving around the nucleus, means they also started to accelerate, right? That is the main reason, that is the main thing, right? Yes. So whenever they are emitting or they are accelerating, so the electrons revolving around the orbit should continuously emit the radiation also. Since they are accelerating, they should consider as they are emitting the radiation also, as per the Maxwell theory. What happens means, as a result of this, what will be going to happen? They will be slowed down. They will be rotating. They will be having this particular acceleration, and they will be emitting the particular radiation also. As a result of this, what happens? It slows down and would not be longer able to withstand the attractive force of the nucleus. Whenever they rotate, they accelerate, and they do the radiation, they emit the radiation, and as a result of this, they collapse into the nucleus. They have to do that. But what happens? It's not happening in the particular electrons. It's there in their place only. So it was not able to explain by the Rutherford. Clear, everyone? Could you please tell me in English, Pooja? I'm not good in Hindi. मैम 12th महीने कोई बैच बाई नहीं किया मैम, आपके क्लासेस को फॉलो कर अपने 11th के बैकलॉग कवर कर सकते हो फॉर माय नीट एग्जाम. Okay, I got it. What is the content? But okay, 12th you didn't attend. You are not in. You are 12th है. You are not attending any कोई पेड बैचेस आपके के फॉलो करके अपने के 11th को बैकलॉग कवर कर सकते तो. Well, I am not. I will try to do it. Okay, I'll try to do it, Pooja. Okay. So, but we know that atom is stable. So, what happens means that particular one, see, nothing is there, children. When the electrons are revolving around, they loses their energy, or they loses they emits the radiation, and they loses everything, and they have to collapse into the nucleus because they will be attracted by the nucleus as per the Maxwell theory. But that is not happening in this, and because it is electrically, it's stable, there is no problem also. But Rutherford was not able to say why it's not explaining, or why it's not possible. That Rutherford was not able to say it. That is also a major drawback of the Rutherford model of atom. Now comes the Bohr model of the atom. So here comes our Bohr model of the atom, which is actually explains about this. Okay, it was actually based on they actually hand to hand with the Planck's model quantum theory, and he found out the Bohr model. This particular Bohr model of atom. So he said that electrons in atom is revolving around the nucleus in a certain path which is called as the orbits. So what happens means, first he was said that okay, it's not like they are having in a circular path only, that is very precise one. They are in the particular circular path which is called as the orbit, and the electrons which is moving in the orbit, they revolves in a particular orbit. They do not lose or gain energy. There is no transfer of energy happening in this particular electrons which is revolving in their own orbit. Okay, and therefore the orbits are called as the stationary orbits, and only those orbits are permitted which in the angular momentum which is equal to mvr. Momentum is equal to mass into velocity, and your angular momentum mvr, that is they should be the integral multiple of nh by h by 2 pi. H by 2 pi. So those are the angular momentum, or those are the orbits which allow this particular one is going to be there. Clear everyone? Okay. So when electron jump from in one orbit to another, you can see that this is going to be the particular one. When the electron is jump from a one orbit to another orbit, what happens? There should be, it will be absorb or emit energy. There, see, for the jumping to some other orbital, they should either absorb the energy or they should okay. Though, so when electron jumps from one place to another place, what happens? Okay, ma'am, could you increase your volume? You're not able to hear my voice. Okay, so what happens means, as long as the electrons are there in the orbital, it's not problem. There is super, everything is fine. But whenever they have to jump into another orbital, or they have to, it's in the lower orbital or higher orbit, they have to either absorb or emit the radiation. Clear everyone? Clear? That is the particular one. Okay. Now, when an electrons jump from a lower level of lower level to higher level, from the lower level to the higher level. Okay, from the lower level to the higher level, when the electrons are jumping, we can say that they have to absorb the energy which is equal to E2 minus E1. Clear? Clear everyone? Clear? When the electrons is coming back to the original position, they have to lower level, which is they have to emit the same amount. So when they goes to the higher one, they have to they are going top, so they have to more energy. They have to absorb the energy. They have to absorb the energy, and when they come back to together, that particular one, they have to release the energy also. Clear? Clear? Okay, that is something which is comes under this category. Okay, so we can say that the particular mu is equal to E2 minus E1 by h by mu now. So we can say that mu is equal to E2 minus E1 by h. So now comes the merits. Merits one was he can explain the stability of the atom. He was able to explain. They help in calculating the energy also. They help in calculating the radius. Our radius is equal to 0.059 into n2, where n is the 1, 2, 3. They will ask you, okay. So they were able to find out the radius, they were able to find out the particular energy, and they were able to analyze the stability also for the atom, and it explained the hydrogen spectrum also, and they could explain the simultaneously the appearance of the large number of lines in the hydrogen spectrum also. He can explain everything. But there are some demerits of Bohr model. See, basically he explained all the demerits of the particular Rutherford model, but there was some problems with this particular one, with the Bohr model, which was he didn't explain the line spectrum of the multi-electrons. They only explained about the hydrogen only, not about the multi-electrons. So it could not explain the splitting of the spectral lines under the influence of the magnetic field. There are Siemens and the Stark effect is there, na? That he was not able to explain. And shape of the molecules was not able to explain. Shape of the molecules, which is formed by the atoms, will be joining and they will be forming the molecules now. How the shape, that is not explained by the Bohr model. And do not explain the fine structure also. Spectral lines, which is in the hydrogen, that is also not explained by the Bohr model. They do not explain the fine lines of structure which is produced by the hydrogen spectrum. Now comes your de Broglie wave equation, which is considered under according to the wavelength, that is lambda, is associated with a particle of mass m moving with a velocity, is given by the equation lambda is equal to h by mv, or lambda is equal to h by p. So how this lambda and this is connected? I'll tell you. Derivation. Okay, derivation is this. Children, I will just tell this derivation. 1 second. So you can clearly understand that. You can understand that. So there are two equations, right? Two equations are there. One is see, as per the, I will write this. See, there is two equation. E is according to the Max Planck H H mu, right? And we know one more equation which is equal to, one second, I will write this here. First equation, E is equal to, which we already know, E is equal to hc by lambda. Am I right? 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 And another equation also is that E is equal to, as per the E is equal to mc square. You studied it in the chemistry, physics, right? Mc square. As per this particular Einstein mass energy, E is equal to mc square. So, there are the two equations. One is E is equal to hc by lambda. One is E is equal to mc square. Now, when we are equating all these two, we can say that hc by lambda, hc by lambda is equal to mc square. Which means I can say h by lambda is equal to mc. Am I right? Because we cut this one, right? So we can say that mc. Now I have to take the lambda. H by lambda is equal to mc. That is something which comes under this category. H by lambda is equal to mc. Now if I want to take the lambda is going to be h by mc, right? Correct? This is basically mass into velocity. C is actually the velocity, right? Right. Are you able to hear me, children? You are not able to hear me? You are not able to hear me? What happened? Can you hear me? One second. Arjun, my- Am I audible now, children? Am I audible now? Yes. Am I audible now? Is everything is fine? Am I audible now? Everything is fine. Okay. So now listen. Lambda is equal to h by mc, which is lambda is equal to h by mv, which is equal to h by p, which is momentum. So I can say this h by p, which is actually, I so told you, c is equal to velocity of the light, h by p, which is going to be p is the momentum, mass into velocity. So I can say that this is the de Broglie wave equation and lambda is called to be de Broglie wavelength. Clear, everyone? Clear? Now comes the Heisenberg uncertainty principle. Heisenberg uncertainty principle is, it's tell that it's impossible to measure both the position and the velocity simultaneously. We cannot for a particle simultaneously we cannot determine the position and we cannot determine the velocity also, the position and the velocity of a particle simultaneously. That is something comes under the category of this particular Heisenberg uncertainty principle. So as per it's mathematically denoted as delta x. Delta x is basically it is actually the position and p is the momentum, which is equal to h by 4 pi. This is the particular delta p is the particular uncertainty in the momentum, and this is the uncertainty in the position. Uncertainty in the position and uncertainty in the momentum, which is greater than or equal to h by 4 pi. So what is Heisenberg uncertainty principle? It states that we cannot determine the position or we cannot determine the position and the momentum of a particle simultaneously. It is impossible. So that is something comes under the category of the Heisenberg uncertainty principle. Now comes the Schrödinger wave equation. So Schrödinger wave equation is something which is this, which is going to be your xyz is the, you can have the Schrödinger wave equation. This is basically xyz are the Cartesian coordinates. This E is the total energy, I can say that. Okay, total energy. V is the potential energy. M is going to be the mass. And I can say that H is going to be the Planck constant. And this is going to be the wave function. This is wave function. Okay, d square wave function divided by dx square plus d square wave function divided by dy square. Clear? That is something comes under the category of this Schrödinger wave equation. This is a presentation. Please do have a note of it. Isn't my mama audible, children? Clear, everyone? Okay. Now comes the orbital and orbit difference. What is the difference between the orbit and orbital? What are the difference, basic difference about the orbit and the orbitals? So the orbit is basically, you have studied it in your smaller standards and all. Orbit is something which we can say that it is well defined circular path which is revolving around the nucleus, right? Which is revolving around the nucleus. Orbital is something which is the region of the space around the nucleus where we can see high probability of electrons. So there is a chance of seeing high probability of the electrons. That is something comes under the category of orbitals. So orbit is something which is, there is electrons are there, which is what is a particular definite correct circular path where the electrons is revolving. Orbital is something we can see the highest probability. So basically I can say that orbit is there. Inside the orbit you will be having the orbitals. There you will can see the maximum probability of finding an electron. Clear everyone? Clear? It is represented as the planar motion of the electrons, and it is represented as the three-dimensional motion. This is actually the three-dimensional motion, and it is maximum number, shell number. Shell, we can say that 2n square is the number of electrons which can accommodate. Here we can say that 2 electrons. In an orbit we can contain only 2 electrons. Clear? For example, if you have the shell as n is equal to 1. If you have the shell as n is equal to 1, we can say that only 2 orbitals will be there. Only one orbital will be there, okay, which is s orbital. If you have n is equal to 2, we can say that 2 orbitals will be there, total 4 electrons. They will be having 2 orbital, which is s and p. Clear? And if they are considering about the s orbital, and separately we are considering s orbital is going to be 3 atomic orbitals will be there. Clear? So that is something orbit and orbital. They are circular in shape orbit. Orbital will be having, orbital have different shapes according to the, they have the spherical, p orbital, double dumbbell shape, everything. Clear? Yes, I am from the south. How did you understand it? Concept of well-defined orbits are against uncertainty principle. Here it is according to the uncertainty principle. What is uncertainty principle? It was impossible to determine the position and the momentum. Clear? Now comes the orbital. So I told you orbitals are the set of numbers which comes under the category of the quantum numbers. You have the quantum numbers. So quantum numbers are basically which energy, size, shape, orientation, all these things, energy, shape, size, orientation, all these things will be comes under the category of these electrons, and we will be finding out the particular electrons. Okay, so if we can say that in order to specify energy, size, shape and orientation of the electron orbital, the 3 quantum numbers are required. So in order to find where the particular electron, what is the shape of the electron, what is the size of the electron, what is the energy of the electrons, we require quantum numbers. We will be starting, or we will be studying it from the quantum numbers. Clear everyone? Thus each orbital in an atom is designated to have a set of quantum numbers. They should have a set of quantum numbers. Then only we can understand which orbital is that, what is the properties of that, what is the say, shape, size, everything. Clear? Okay, so now comes our first quantum number, which is principal quantum number. It's represent the main shell. N is there now. It's represent the main shell, and it determines the energy of an electron. What is the energy of the electron is determined by the principal quantum number, and it is denoted by the letter N. We can say that instead of N is equal to like K, L, M, N is there now. N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4. Clear? So as the value of N increases, what happens, children? The electron gets farther away from the nucleus. For example, N is equal to 1 means K, N is equal to 2 means it's L, N is equal to 3 means it's going to be M. So that is something comes under the category of principal quantum number. Principal quantum number. Clear everyone? Okay, fine. Next one is your magnetic. For example, I will give you N is equal to 1 means one second. Okay. Next one is your angular quantum number, or azimuthal quantum number. Okay, angular quantum number or azimuthal quantum number, which is denoted as L. Okay, this is denoted as L. Clear? So first one, azimuthal quantum number is denoted as the angular, that is basically determines the angular momentum. I told you now, it actually based on the quantum, it's actually based on the Heisenberg uncertainty principle. So it's like that, the quantum number determines the angular momentum of the electrons, which is denoted by the L. This is L, children. The value of the L gives the subshell electrons, which will, I will tell you this is easily. When L is equal to 0, I can say this is going to be S subshell. L0, it is going to be S. L is equal to 1, going to be sp, 2 means spd. Clear? Clear? So L may have all possible whole number from 0 to n minus 1 for the each principal energy. So I can say that depending upon this, for n is equal to 1, L can be only 0. So n is equal to 1, only S subshells are there. Na? So if it is L is equal to 0, n is equal to 1 means I can say that only one subshell, which is oneness. Clear? That is going to be oneness. Okay, for n is equal to 2, n is equal to 2, I can say that L is going to be 1, which means I can say that they are going to S and P also. 2S and 2P is going to be happening, right? 2 and Ankha Misriya, 2S and 2P is going to be happening because n is equal to 2. N is equal to 2 means it is going to be having 2. So S means I can say that L is equal to 1 means 0, and I mean 2SP will be having it. L is equal to 1 means it's going to be having S and P. N is equal to 2 means second orbital. So 2S, 2P. Clear? For 3, L can be, values can be 0, 1, 2, which means I can say that n is equal to 3 means L is going to be 2, which means SPD, which is 3S, 3P, 3D. Clear? 3S, 3P, 3D. Okay, next one is your magnetic quantum number. It is denoted as M. It represents the orientation. What is the orientation of the electrons? We will be discussing. So different orientation will be, the different orientation are called as the orbitals. So we can say that the positive value, for example, the positive value of M ranges from positive 1 to minus 1. Positive 1 to minus 1, which includes a 0 also. So we can say that for L is equal to 0, I can say L is equal to 0 means it's S orbital, and M is equal to be 0. It implies that the subshell has only one orbital, which means 1s, which is only one orbital. Okay, now L is equal to 1 means I can say that they are going to have S and P for the subshells, right? So now I can give the value. The M is going to have plus 1, 1 now, plus 1, 0, plus 1, right? I mean not plus 1. I can say the 1, L is equal to 1 means I can say that M value is minus 1, 0, plus 1, which is going to be 3, right? The subshell, it implies the P subshell has 3 orbitals. Are you getting my point, children? Yes. Now L is equal to 2 means they can have 5 orbitals, 5 values, which is minus 2, minus 1, 0, plus L is equal to 2 now. So minus 2, minus 1, minus 2, minus 1, 0, 1, 2, which means 5, which means D is going to have 5 orbital. D is going to have 5 orbital. L is equal to 3 means you are going to have half orbitals also. So we can say that it is going to have minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, which is going to have 7 orbital. So in short, I can say that S is going to be having, in short, one second, then what is it's not working? In short, I can say that if S is going to have 1 orbital, P is going to have 3 orbital, which means this is going to be have 1, this is going to have 3, D is going to have 5 orbital as per the M, and F is going to have 10 orbitals. I mean 6 orbitals. I'm not able to take in another page for this. 1, 2, 3, 4. 1, 2, 3, 6, 7 orbitals. 1, 2, 3, 6, 7. Okay, this is maximum electrons is 2. Here it's going to be 6. Here it's going to be 10. Here it's going to be 14 electrons number. Okay, next come is the spin quantum number. It tells about the direction of the spin of the electrons, which means one is that is clockwise or anti-clockwise. So we can say that they have plus 1 by 2 and minus 1 by 2. The plus 1 by 2 indicates the clockwise, minus 1 by 2 indicate the anti-clockwise. Now comes the shape of the orbitals. So S orbital shape is basically, we can say that they do have the S orbital is L is equal to 0. They do have the M is also 0. So we can say that there is only one orbital, which is S orbital. We can say that S orbital are spherically symmetrical. You just want to understand this only. They are they are actually spherical in shape. They are actually spherical in shape with a note. Now p orbital, we can say that L is going to be 1. Okay, so M is going to be plus 1, 0, 1, which means they will be going to have 3 orbitals. Am I right? Yes, they're going to have 3 orbital, p orbital. So px, py, pz. What are the symmetries they are going to have? They are designed. They will be having px, py, and pz. So px, py, and pz will be having the symmetry. They are having the shape of dumbbell shape. They are having the shape of dumbbell shape. So it will be the px. This is the py, and this is going to be the pz. Okay, px, py, and pz. They are going to have as per the m, minus 1, 0, plus 1, 3. Okay, next is d orbital. D orbital for d orbital. This is d. Okay, for d orbital, I can say that for d orbital, we can say that L is 2. It's going to be plus 2, plus 1, 0, minus 1, minus 2. What are its children? Plus 2, plus 1, 0, minus 1, minus 2, which means I can say that there should be together how many 5 orbitals are there? So 5 orbitals will be there in the plane dxy, dyz, dxz, dx square minus y square, dz square, xy, xz. I mean xy, y, dxy, yz, x, dxy, yz, xz, dx square minus y square, dz square. These are the orbitals which will be there. That is double dumbbell shape, which will be doing double dumbbell shape. I repeat, xy, yz, xz, x square minus y square, and z square. Clear, everyone? Clear? So this is going to be dxy. Okay, and this is going to be x set. This is going to be the x set, and this is going to be the y z. Okay, now comes the z square, means it should be in the z axis, right? It should be in the along through the axis, or not between the axis. These are all between the axis. This is basically between the axis x, y, x, z, and y, z, right? But z square minus y square and z square, especially z square and x square minus y square are along the axis. Clear, everyone? Now comes the rules for filling the orbitals. How can we fill the orbitals? So first rule is basically our Pauli exclusion principle. Pauli exclusion principle is telling that no two electrons in an atom can have the same value for the 4 quantum number. So in an atom, only no two electrons, they should not have the same value for the quantum number. Thus in an atom, the 2 electrons may have a maximum of 3 quantum numbers, the same, but the fourth must be different. Actually there should be 4 quantum number. There is at least 3 has to be same, or I mean at least 3 can be, maximum of 3 can be same, but one has to be different. For example, you have the K subshell, which is K shell is equal to 1. N is equal to 1 means L is going to be 0, and M is also going to be 0. S is going to be plus 1 by 2. N is equal to 1. N is equal to 1 means we can say that L is equal to 0. M also going to be 0, because 0, if L is equal to 0, of course M is also going to be magnetic, also going to be 0. Spin is going to be minus 1 by 2. So I can say that this is going to be different. So at least 3 can be same. Okay, 3 quantum numbers can be same. The last one has to be different. That is something comes under the category of the Pauli exclusion principle. On the basis of this Pauli exclusion principle, it also considers that the orbitals have maximum of 2 electrons in a particular orbit. On orbit, for example, this is an orbit, means they can maximum have 2 electrons in it. Okay, which means S subshell can have 2 electrons, P can have 3 orbital, which means 6 electrons. Am I correct? D can have 5 orbital, which is 10 electrons. F can have 7 orbitals, which is going to be 14 electrons. This is as per the Pauli exclusion principle. Now comes the Aufbau principle. Aufbau principle states that the electrons are filled in the various orbital according to their increasing order of their energy. So Pauli exclusion principle was we should not have more than same value for the quantum numbers. Then Aufbau principle says that the electrons has to arrange, or the electrons has to fill according to the increasing order of their energy. For example, the energy order is that 1s, 2s, 2p. Okay, listen carefully. This 1s means I can say that this is going to be n. N is equal to 1. Here, if the n is equal to 2, I can say that 2 orbitals will be there. Here, the L is going to be 1. L is equal to 0 here. 2s and 2p. If n is equal to, one second. N is equal to P means there is 3D also, children. N is equal to 3 means we can say that L is going to be equal to 3. L is going to be equal to 2. Correct? M is going to be equal to equal to 6. correct? I mean, in the 3D means L is equal to 2 means -2 plus -2 -1 0 1 2, which is going to be 5. Clear? So this is all about the d orbital also, which is 3s also. Now comes in another important factor here, children. You may think that 3D comes first. Okay, the difference between there is a 3D and 4s. So as I know, 1s, 2s, 1s, 2s, 2p, then 3s, 3p, 3D you expect, then you expect the 4s. But because there is a slight energy difference, 4s is having less energy. So what happens means, instead of the 3D, 4s is going to fill first, then 3D comes. Clear? That's why 4s, 3D, then 4p. Before 5D, we will be having 5s. Then you have the 4D. Then you have the 5p, 6s. Before this, you will be having the 4f instead of 5D. Clear? So this is how you will be filling the electrons. So you always remember, if S is equal to 1 orbital will be there, P is equal to 3 orbitals, total 6 electrons will be there, D means it's going to be 5, which because we will be having, if the D orbital comes means L is going to be 0, L is going to be 2. So -2, -1, 0, 1, 2. Clear? So the M is equal to 5 will be the, so it's going to have the 5 atomic orbital, which is will be having 10 electrons in that. Okay. So this is the order, children. 1s, 2s, 2p, 3s, 3p, 4s. Instead of 3D, you will be having 4s filled because 4s is having less energy than the 3D. Clear? S, SP, SPD, SPDF. SPDF. Okay, SFTB, no. Misra. S, SP, SPD, SPDF. Clear? Clear? Okay. Now comes the Hund's rules of maximum multiplicity. Hund's rule states that the electron pairing will not take place in the orbital on the same energy until each orbital is first singly filled, which means I will tell you what is this basically. We have to, the electronic configuration. So one second, I will tell you. So what happens means, they have to fill, the electrons pairing will not take place in the orbital of same energy until each orbital is first singly filled with a parallel spin, which means, for example, you have the you have the p orbital, 2p. Okay, you can understand that there is 3 orbitals. 2p, there is 3 orbitals. Okay, 1, 2, 3. Am I right? 1, 2, 3. Okay. Okay, 3 orbital you will be having 1, 2, 3. I mean, one second, children. Someone has messaged me there, that's why I just, okay, 3 orbitals you have. Okay, now I'm telling you there is 4 electrons is filled in the 2p. Okay, so we cannot fill 1, 2, 3, 4, not like this. We have to fill it accordingly. We can say that they should have the same energy in the first time. So 1, 2, 3. Then only we can fill the 4. Okay, we cannot fill it like this, 1, 2, 3, 4. This is not possible. This is wrong. This is the correct way. That is something comes under the category of Hund's rule of maximum multiplicity. Clear, everyone? So this is the electronic configuration of this. 1s 2 you will be having, 2s2 you will be having, then beryllium 1s2 2s2. Now comes the boron. It should be in the px1, px, that is p orbital boron, they will be having 1 electrons. Now when comes to the carbon, the p orbital will be having 2 electrons. Okay, px1 and px11 and py11. Now what happens means, you cannot fill it like this. 1s2 2s2 2p2, you cannot fill it like that. In the px itself, you cannot fill it 2 electrons. You have to fill it all the things and the same energy, then you have to complete it again. Okay, clear? For example, carbon, you cannot fill it like this. This is wrong. For the carbon, you have to fill the px orbital, p orbital like this. For example, px, they should have 1. Py also, they should have 1. Px should not have 2 electrons as like this, because it's already Hund's maximum rules of multiplicity. Okay, clear? Same thing happens to the nitrogen, fluorine, carbon, neon. Clear, everyone? So this is all about this particular atomic structure. So I know that we taken a few more minutes. That's why everyone is calling me, I guess. One second. Okay. So I hope the session was useful for you guys. Okay, so this is the something which you have to keep in your mind. Okay, this is something which you have to keep in mind. You cannot fill it like this. You, the orbitals, same orbitals will be having that. These do have the same energy. 2p t p x y p y p y p z, right? They do have the same energy. So what happens? You have to first singly they have to fill it, because this is one. Singly they have to fill it. Then you have to fill it again. Well, for example, 4 means you cannot fill 1 2 1 2 here. You have to fill the 3 first, which will be having same energy now, because this is 2px, this is 2py, this is 2pz, which have the same energy. So they have to singly, we have to fill it. Then we can fill the fourth one. Clear, children? Ah, exactly, Maria. Yes, children. Yes, exactly. Okay, so I hope the session was useful for you, children. Please do let me know in the comment section. Okay, so next class we will be coming with the periodic classification. Okay, we have a time limit of 2 hours only. That's why I'm not able to take in depth. Okay, I have taken everything whichever is required for you. Okay, so next session we will be discussing about the periodic classification of elements. Okay, I hope you understand everything what I taken. Please do let me know in the comment sections. Okay, bye bye. Thank you.